70 minutes for the presentation and another 3 minutes for question and answering. And for the 2 demo paper, you will have 80 minutes presentation and another 2 minutes for question and answering. So for the first paper, Yueming Wu from Huazhong University of Science and Technology will present their study on clone detection based on semantic token analysis. So let's welcome Yueming to give the talk. Thank you.
Hello everyone, good morning. It's my honor to be here to present our paper. My name is Yueming Wu. I'm from Huazhong University of Science and Technology in China. Our paper is cooperated with Professor Liang, who is from University of Texas at Dallas in America. The automatic detection of code clone is an important research problem. There have been proposed many tools for achieving the goal, such as some open source tools and academic research projects. Commonly, code clones are classified into 4 types based on the syntactic or semantic levels differences. The first 3 types of clones are syntactic clones, while the last type of clones characterize semantic clones. In practice, studies related to code clone detection can be classified into 5 main categories. That is, the text-based, the token-based, the tree-based, the graph-based, and the matrix-based methods. Text-based and token-based methods cannot detect semantic clones, while tree-based, graph-based, and metric-based techniques have the ability to handle semantic clones. In general, token-based methods are the most scalable on code clone detection. However, because of the lack of extraction of program semantics, they cannot handle type 4 clones. To address the issues, researchers conduct program analysis to distill the semantics of code fragments into graph representation and perform graph matching to measure the similarity between given codes. Compared to token-based techniques, these graph-based detectors can achieve higher effectiveness on detecting semantic code clones. However, they cannot scale to big code due to the heavy wait time consumption of graph matching. Therefore, we raise a research question. Can we and how to combine the scalability of token-based techniques with the accuracy of graph-based approaches to detect semantic code clones? To answer the question, we mainly address 2 challenges. That is, how to transform the high-cost graph matching into succinct token analysis while preserving the graph details, and how to design a scalable yet accurate similarity computation process to handle semantic clones. Our paper makes the following contributions. We propose a novel technique to transform CFGFN method into certain semantic tokens. We design an automatic system to combine the scalability of token-based approaches with the accuracy of graph-based tools for semantic clone detection. We conduct a comprehensive evaluation on Google Code Cheng and a big clone bench dataset. We first introduce the motivation of our paper. Source CC is a token-based clone detector which can scale to very big code. It uses overlap to measure the similarity. For instance, given 2 methods M1 and M2, the overlap similarity is calculated as the ratio between the number of same tokens shared by M1 and M2 and the maximum number of tokens in M1 and M2. We leverage a simplified example big clone bench to illustrate how source CC computes the similarity of 2 methods. These 2 methods are both to calculate the greatest common divisor of 2 numbers. We first conduct lexical analysis to parse the methods into several tokens. The analysis results show that the number of tokens in method 1 and method 2 is 38 and 32 respectively. We observe that there are 9 same tokens shared by these 2 methods. In other words, the overlap similarity of method 1 and method 2 is computed as 50%. The default setting of similarity threshold in source CC is 70%, which means that source CC reports two methods as a clone pair only when the similarity of them is larger than 70%. In this case, source CC will cause a false negative by not reporting methods in method 1 and method 2 as a clone pair. In order to detect the semantic code clone, we plan to extract graph representation of them. More specifically, we leverage suit to obtain the CFGs of these two methods. After obtaining the CFGs, we use the degree of all basic blocks to maintain the graph structures. In particular, we first dig out the degree of each basic block and then assign the degree to each token in the basic block. Finally, we sum the degree of the same token in all basic blocks and treat it as the weight of the token. For example, the degree of basic block 1 and basic block 2 are 3 and 2 respectively. Then the weight of a label 0 will be computed as 5. After obtaining the corresponding weight of all tokens, we compute the overlap similarity by weight instead of by the number of same tokens shared between two methods. In this way, the total weight of all tokens in CFGs of method 1 and method 2 are 112 and 79 respectively. After overlap analysis, we find that the weight of the same token shared by these two graphs is 70. Therefore, the overlap similarity can be calculated as 62.5%, which is greater than 50%. However, code clone detection may not be accurate if we only consider the degree of a basic block as the weight in the graph. For example, suppose that there are two CFGs, namely CFG1 and CFG2. The number of basic blocks of these graphs are 220 respectively. The degree of two basic blocks are both 10. It is obvious that the weights of B1 and B2 are different because B1 in CFG1 is associated with 5% of the other basic blocks, while B2 in CFG2 is associated with 50% of other basic blocks. Therefore, we compute another weight of tokens by normalizing the sum of degree. In this case, the overlap similarity will be computed as 80%. In other words, transforming a graph representation into tokens with normalized degree may be a great candidate for handling semantic clones. Based on the observation, we propose our approach, SCDetector. SCDetector consists of three main phases: static analysis, centrality analysis, and the clone detection. The goal of static analysis is to extract the control flow graph of a method. Specifically, we leverage suit to complete our static analysis. After obtaining the CFG of a method, we then apply centrality analysis to transform the graph into certain tokens with graph details. Centrality concepts were first developed in social network analysis, which quantified the importance of a node in the network. Centrality measures are very useful for network analysis and have been applied in many different areas, such as biological network, co-authorship network, and transportation network. In practice, there has been proposed many different centrality measures, such as degree centrality, closely centrality, and car centrality. As a matter of fact, previous study has validated that degree centrality can achieve the highest scalability while maintaining high effectiveness on graph analysis among many centrality measures. Therefore, we select degree centrality to begin our centrality analysis. Given our CFG, we first extract the degree centrality of all basic blocks in the graph. A basic block is composed of several tokens, which can be obtained by lexical analysis. After degree centrality analysis, we assign the corresponding centrality to all tokens in the basic blocks and compute the total centrality of the same token in different basic blocks. In brief, the input of centrality analysis is a CFG, and the outputs are tokens with graph details called semantic tokens. After centrality analysis, the CFG of a method is transformed into certain semantic tokens. In reality, these tokens are indeed words. If we sort them according to the first letter, then these words can be regarded as a sentence. Therefore, we can apply techniques in the field of natural language processing to encode the sentence into vector representation for efficiently similarity computation. In this part, we aim to identify whether two methods are clone pair. To detect the code clone pairs, we propose to use a Siamese network, which is best suited for similarity computation for two objects. Siamese neural network is a class of neural network architectures that contains two identical subnetworks, which means that they have the same configuration with the same parameters and weights. Previous studies have validated that GRU can achieve almost the same performance as LSTM, while requires less training time on processing the same task. Therefore, we prefer GRU in our deep learning models. The input of GRU network are certain semantic tokens obtained by centrality analysis. We first train embeddings of tokens using word2vec to convert the token into a fixed length vector whose dimension is said to be 100. After multiplying by the corresponding total degree centrality, the semantic vectors are then fed into two identical GRU subnetworks. Finally, a comparator network takes inputs of these two subnetworks' outputs to compute the distance. The output of the trained Siamese network is the probability that two input methods are clone pair. We claim that two methods are clone pair if the value is above 50%. To examine the capability of SCDetector on detecting code clones, we conduct several evaluations. Specifically, we begin our evaluations by using two datasets, Google CodeGen and the Big Clone Bench. Programs in Google CodeGen are collected from online programming competition held by Google. In Big Clone Bench, each clone pair is manually assigned a corresponding clone type because of the ambiguous boundary between type 3 and type 4. These two clone types are further divided into three subcategories by a similarity score after normalization, as follows: strong type 3, moderately type 3, and weakly type 3. We run all experiments on the server with 8 cores of CPU and the GTX 1080 GPU. We use the widely used metrics to measure performance of SCDetector. In our paper, we totally compare SCDetector with 4 state-of-the-art code clone tools, which are SourceCC, Deqing, RTVN, and AST2020. We first present the detection effectiveness of SCDetector on code clone detection in Google CodeGen and the Big Clone Bench. We ignore the result of AST2020 in Google CodeGen dataset because it takes a lot of time and some errors occur when processing code pairs in Google CodeGen dataset. From the results in these two tables, we can see that SCDetector can achieve the best effectiveness on code clone detection compared to SourceCC, Deqing, RTVN, and AST2020. In order to check the effectiveness of semantic tokens and Siamese network on detecting semantic clones, we conduct several single-factor experiments. In the first experiment, we take inputs of the original tokens obtained from the source code of a method by lexical analysis into a GRU encoder. Given two methods, the outputs of the GRU encoder are two vectors. After obtaining the similarity of two vectors by analyzing the cosine distance between them, we claim that the two methods are clone pair when the similarity is greater than 70%. In our second experiment, the original tokens are fed into a Siamese network, including two identical GRU subnetworks. The output of the Siamese network is the probability that two input methods are clone pair. These two methods are detected as a clone pair if the probability is larger than 50%. In our final experiment, we implement SCDetector, which means that methods are first transformed into certain semantic tokens and then fed into Siamese GRU network to train and test. Similarity, if the probability is larger than 50%, these two methods are treated as a clone pair. GRU networks used in these three experiments are the same network. The experimental result indicates that the attachment of graph details to tokens and the adoption of a Siamese network are both effective on detecting code clones. Our final part focuses on the runtime performance of SCDetector and for comparative systems. In order to test the scalability of these code clone detectors, we randomly select 1 million code pairs from Google Code Cheng dataset as our test objects. We ran autos on these randomly selected code pairs 3 times and report the average time. For deep learning-based methods, the complete procedure consists of model training and model testing. This figure shows that SCDetector requires more time to detect clones compared to sources. However, it is faster than ASTN. ASTN requires more than 2,000 seconds, while it only takes 139 seconds for SCDetector to complete the prediction. Similar to prior approach, SCDetector also suffers from several limitations. First, we leverage shoot to generate the safety of a method. However, shoot requires to successfully compile the given code first, and then the safety can be extracted. It is a reason why we cannot use all the files in big clone bench dataset to commence our evaluation. Second, SCDetector can only detect the method level code clones and cannot handle clones in other code granularity units. Third, copying a method and then pasting with large number of edits can cause false negatives by SCDetector, since the safeties of the original methods and the pasted methods are significantly different. In this paper, we propose a novel idea to combine the scalability of token-based methods with the accuracy of graph-based techniques for semantic code clone detection. Based on the idea, we design an automatic code clone detection system. To validate the ability on semantic code clone detection, we conduct a comprehensive evaluation on Google Code Cheng and Big Clone Bench datasets. Thanks.
Okay, thanks, Yueming. So we're waiting for some questions. So I will begin with my first question. So overall, it's a very interesting and excellent paper. So I noticed the performance of your tool is already very high. For example, the F1 score in the Big Clone Bench is almost 1. So do you have any suggestions? For example, if we still want to continue to do clone detection research, do you have any directions we can try to improve your approach, or other areas we should investigate? Because your performance is almost perfect.
Okay. Our performance is our proposed method is efficient because we adopt the social network analysis we apply a social network analysis to detect the code clones. Therefore, as a matter of fact, social network analysis can produce even millions of loads, such as Twitter, So therefore, I suggest if we can apply social network analysis on the graph analysis to detect the semantic clones, the efficiency may be mitigated, maybe more efficient.
Okay, so for the second question, because you use a lot of social network analysis, and in your paper you focused on the centrality analysis. So I'm wondering, because in social network analysis they have also other analysis techniques like measure the in degree, out degree, and also they analyze the clustering coefficient, this kind of analysis. So why do you only focus on the centrality here in your study?
The first reason is that some previous studies has validated that centrality analysis is effectively on graph analysis. And the second, centrality analysis is very efficient on graph analysis. And this is the two